Let's have a look at some of the questions from problem set 5. In our first example here, we are adding HI to an alkene. This should look familiar, so what we're doing is a hydrohalogenation reaction, which is going to follow Markovnikov's rule. Again, Markovnikov's rule is less E, more nu, meaning that the less substituted carbon will get the electrophile and the more substituted carbon will get the nucleophile. So let's identify first our less substituted and more substituted carbons. We look at what's directly attached to our sp2 carbons, and the one on the left has a methyl group and a hydrogen, the one on the right has two methyl groups. So the one on the left here is our less substituted, and the one on the right is going to be our more substituted carbon. So now we just do the reaction. We'll draw out our carbon skeleton first. Okay. Now, the electrophile is going to add to the less substituted carbon, which we've already identified as the one on the left. So our electrophile, in this case is hydrogen, will add there, which means that our nucleophile is going to go to the more substituted carbon right there. And that is our answer for the first example. Okay, now let's look at our second example here. So first what we are doing, we are adding H2O and H2SO4. So this should look familiar. We are doing the hydration reaction, which also follows Markovnikov's rule, again, which is less E, more nu. So let's first identify our less substituted and more substituted carbons. So the carbon on the right is connected to two hydrogens. The carbon on the left is connected to a ring and a hydrogen, so it's going to be more substituted. So at first, we might initially assume that our product may look like this. However, that's wrong. So now we ask, why is this not the product that we get? Well, first, we can redraw this structure here to show all the hydrogens in the ring, which could or could not be helpful. In this case, I think it is helpful. So you can notice that we have a hydrogen right there that can actually shift and make a difference. So at first, if we break the double bond like we did with the wrong answer here, we get a carbocation, which is no surprise, that's what we've been getting. So we get a carbocation intermediate. So now let's classify our carbocation intermediate. So whenever we do this, we look at where our carbon with the positive charge is, and we ask how many other carbons is it attached? Well, this one's attached to 2 carbons, so this is going to be a secondary carbocation. Now, if we can shift this hydrogen up to this carbon, will that give us a more stable carbocation? Well, if we do that, let's now look at this carbocation intermediate over here, and let's figure it out. So to how many carbons is this one connected to? It's got 1, 2, 3, so this is a tertiary carbocation. The tertiary carbocation is more stable than the secondary. So we will use this carbocation intermediate to get our final product. So let's get rid of this wrong answer here. Now keeping this in mind, with our carbocation intermediate, we're going to be able to draw our product. Now notice we're going to have 2 things coming off this carbon. So one is going to be our OH group, and the other is going to be our CH2, CH3, or ethyl group. Right, and that's the answer to our second example. Okay, moving on to our next example, we're adding Br2 and H2O. So this looks like a halogenation reaction, and since we have water and we're using Br2, we're going to get a bromohydrin. Okay, again, this is going to follow Markovnikov's rule, less E more nu, except the less substituted carbon is going to get a Br, and the more substituted carbon is going to get the OH group. Okay? Now, also remember that we have stereochemistry in play here. Whenever we're doing these halogenation reactions, these are going to be anti-addition. Okay? Now, since they're going to be anti-addition, that means that our bromine and our OH group need to be anti or trans to each other. So we have to keep that in mind when we're predicting our product here. Okay, so our less substituted carbon is this one, right? So this is our less substituted carbon. That's where the bromine's going to go. Our more substituted carbon is this one, and that's where our OH group is going to go. But now we have to figure out the stereochemistry, and we also have to keep in mind this methyl group that we have on the ring already. If we choose for the bromine to be coming out as a wedge, that means that the OH group needs to be coming off as a dash. So now what about the methyl group? Well, since the OH is going to be dashed, that means that the methyl group is going to come off as a wedge. And that's the answer to this example. Now, there is also another way you can show the stereochemistry. So I'll go ahead and show that one if we do it. But instead of the bromine being wedged, if we chose to do it as a dash, that means that our OH group is going to be coming off as a wedge. And then our methyl group is dashed. So both of these answers show the same stereochemistry, and you have to show the stereochemistry when you predict the products. Okay, let's move on to our next example here. So with this one, we are using metachloroperbenzoic acid. Whenever we see that reagent, we're thinking of epoxidation, as shown here. And you notice what happens is we get a ring with an oxygen in it right where the double bond is. So the two carbons that are involved in the double bond get the ring structure. Now, it's also important to note that we have stereochemistry here. Our stereochemistry is going to be retained. So if we look at the first structure here, our reactant, it's trans, right? So we have to keep that in mind. So we can draw our structure. And then put our ring in it. Like that. That's still showing that we have a trans product, but a way I think about this that makes a little more sense is to show these using wedges and dashes. That way you can clearly see if the groups are trans to each other or if they're cis to each other. But first, remember with this reactant that we do have hydrogens that are not being shown on the bond line diagram like so. Now this is how I prefer to ask. So if we focus on what's going on over here on the left, we can ask, what is pointing down at us and coming out of the plane? Well, that looks like a methyl group. Okay, so let me first draw the ring. So we're going to have two things that are coming out of the plane at us. Two things going behind the plane. So again, in the first one, we asked what is pointing down at us, and we said that is a methyl group. Okay, then what is pointing up and away from us? This hydrogen. So we put the hydrogen on the dashed line that's pointing up and away from us. Now we can do the same thing for the other side. We ask what's pointing down and coming out of the plane at us. This hydrogen here. Okay, so we come over here and put this hydrogen on the wedge. Okay, then we also ask again what's pointing up and away from us. Looks like this methyl group is. So we can put the methyl group right there. And that shows us that we have the trans product. You can see that the two methyl groups are trans to each other. Two hydrogens, they are trans to each other as well. And that's our answer. Again, it's important to show our stereochemistry here. So just for emphasis, this is the trans product. Continuing on with our next example, we see we are adding CH3CH2OH, which is ethanol. So we're adding an alcohol. This is solvation, which again is going to follow Markovnikov's rule, less E, more nu. So let's go ahead and just identify the less substituted carbon. It's the one with the two H's, right? Compared to the other carbon, which has two methyl groups. So that's the more substituted carbon. Now, the nucleophile is going to be our OCH2CH3 group, and our electrophile is going to be the hydrogen. So when we draw this out, keeping the same carbon skeleton, the electrophile adds to the least substituted carbon, which is this one, right, as we identified. And the nucleophile is going to add to the more substituted carbon, which is that one. Now, note that everything attached to this oxygen here came along for the ride. We didn't randomly lose any carbons or add anything, add any more carbons or anything like that. So whatever is attached to that group came along for the ride, and that's our product. Now, this product is an ether. So whenever you're adding an alcohol, you're going to get an ether as your product. Okay, let's move on to our final example here. Now at first, this one can be somewhat confusing because we've added things like HBr, HCl, we've added Br2, Cl2, and so on. We know how to do those reactions. What happens when we have BrCl? Well, first we need to figure out what our nucleophile is going to be and what our electrophile is going to be. So the first question that we can ask is, which one of these, bromine or chlorine, is more electronegative? And if we look at the periodic table, chlorine is more electronegative. It pulls away all that electron density, building up a good negative charge on the chlorine atom, partial negative charge, and a partial positive charge on our bromine. So with that in mind, this chlorine is going to be our nucleophile. Bromine is going to be our electrophile. So it's going to follow Markovnikov's rule, less E, more nu. So if we redraw our carbon skeleton here, less substituted carbon gets our electrophile, which we said here is going to be bromine. And then our more substituted carbon is going to get the nucleophile, which we said would be chlorine. And that is our answer to our example.